All right, part C. At what time where 0 is less than or equal to t is less than or equal to 8, is the amount of water in the pipe at a minimum? Justify your answer. All right, well, let's define a function w that represents the amount of water in the pipe at any time t, and then we could figure out how to figure out the minimum value for w over that interval. So let's just say w of t, so that's the amount of water in the pipe at any given time t. It's going to be equal to, well, we start with 30 cubic feet of water in the pipe at t equals 0. They tell us that right up here. So we start with that much, and then we are going to add or take away some amount. So then it's going to be plus, we're going to sum up from time 0 to time t. Remember, this is a function of t. Well, let's sum up our net inflow times little small changes in time, and we'll sum up all those small changes in time from 0 to t, and that'll give us our aggregate inflow, our aggregate net inflow. So what is our net inflow? Well, you have the function r, which says the rate at which the water is entering, and your function d, which is the rate at which water is exiting. And instead of using t as our variables here, I'm going to use x, since t is already one of our variable, is one of our boundaries of integration. And we can use any variable we want. It's really just a bit of a placeholder variable for the integration. So our net inflow is I'll say r of x minus d of x, and then dx. Once again, this is our net rate of inflow. This is our inflow minus our outflow, so our net rate of inflow times small changes. You could view this as time, although it's x, and then we sum up from 0 to time is equal to t. So this is how much water we are going to have in the pipe at any time t. So let's now think about at what point does w hit a minimum in this interval. And there's three possibilities where w could hit a minimum point. It could hit a minimum right at the beginning at w of 0. It could hit it at the end of our interval at w of 8 at t equals 8, or it could be someplace in between where w is at a local maximum point, in which case the derivative of w will be equal to 0. So let's first evaluate w at the endpoints. So w of 0, well, we know that. That's the bounds are going to be 0 to 0. They even gave that to us in the problem. It's the initial state is we have 30 cubic feet of water in the pipe already. And now what is w of 8? Well, this is going to be 30 plus the definite integral from 0 to 8 of r of x minus d of x dx. And lucky for us, we're allowed to use a calculator, so let's use a calculator to evaluate this. And so let me get my calculator out, and actually let me go see the definitions of r of x and d of x right over here so I can type them in. And what I'm going to do, and there's a bunch of ways, the more advanced you get with a calculator, that might save you some time if you're on the AP test. I'm going to actually define a function that is r of x minus d of x. So everywhere I see a t, I'm going to substitute it. I'm going to use an x instead. And then I could use that later on to integrate it or to solve it in some way. So let's do that. So y1 is going to be 20 times sine of x squared divided by 35, close parentheses, minus, open parentheses, you have negative 0.04 times t to the third power, so I'll write times x to the third power plus 0.4 times x squared plus 0.96 times x, and then I can close these parentheses. So does that make sense? 20 times sine of x squared divided by 35 minus negative 0.04 x to the third plus 0.4 x squared plus 0.96 times x. All right, there you go. I have defined y1, and now I can use that to evaluate different things. So let me now go back here. And so let me evaluate what this is going to be. This is going to be 30 plus the definite integral. I'll go to the math functions. You scroll down a little bit. This is the function for definite integral, function integral. And the function is y1, and I can go to vars, go to my y vars, it's going to be a function variable. So y1 is what I select. I could have typed it in, but this will hopefully save time and I can reuse y1. And my variable of integration is x, and I'm going from 0 to 8. From my lower bound is 0, my upper bound is 8, and let's see, did I type everything in? All right, and then let it munch a little bit, and there you have it. It's approximately 48.544 cubic feet of water at t equals 8. So let me write that, 48.544. So this is approximately 48.544 cubic feet. And now let's see if there's any point in between where W hits a local maximum point, or a local minimum point, I should say. I think I said a local maximum earlier on. I should say a local minimum point. And so if it's at a local minimum or maximum point, really, the derivative of W is going to be 0. So let's see, at what t do we get a zero derivative? So W prime of t, well, the derivative of a constant with respect to t is 0, and the derivative of this with respect to t, and this comes straight out of the fundamental theorem of calculus, this is going to be r of t minus d of t. Where once again, this is a function, we have t as the upper bound, and so we have whatever here that we were integrating, but it's now going to be a function of t. And so in order for this to be equal to 0, we need to figure out, when does r of t minus d of t equal 0? And lucky for us, we've already typed in r of t minus d of t. We've defined that as y sub 1 on our calculator. So let's go back here. And now I can use the solver. So go to math, and then let's see if I scroll up. Let's see, I get to the solver. I could have scrolled down as well. It's right below definite integral. So I go to the solver, and I say the equation 0 equals, and now I could just go to y1. So go to my y variables function. I select y1. So my equation is equal to y1, and I press enter. And now I could put an initial guess for what x value is going to solve that equation. It's really a t value, but I'm using x as a variable here. And now I do alpha, and I click solve here. It's a little in blue you see right above the enter. And it gets to, well, 0 is one of them. Let's see if I can get another one. So let's see if I start at 2, alpha, solve, let it munch on that a little bit. Okay, so this is actually within the interval. So approximately 3.272. So t is approximately 3.272. That's where we have a local minimum point. But now we have to evaluate W there. So we have to evaluate W at 3.272 to figure out if is it truly lower than W of 0. W of 8 is even higher than W of 0. So how do we do that? Well, luckily, we can go back. So second quit. And that should be stored under the variable x. Yep, it's right there. So then we can say, well, let's calculate. We want to calculate the function evaluated when t is 3.272. So our function is 30 plus the definite integral. Go to the math. So definite integral. And once again, we have y1. So let me go to my y variables function. y1, we already defined that as r of x minus d of x. Our variable of integration is x. Our lower bound is 0, and our upper bound is 3.272, which we stored in the variable x. So we can actually, it's a little confusing. This is saying what's our variable of integration. This is the actual variable, this is the actual value for our upper bound. And so let's munch on it a little bit, and we get 27.965. So this is approximately equal to 27.965. So now we're ready to answer at what time t is the amount of water in the pipe at a minimum. We can see that at time 3.272 we have less water in the pipe than either right when we started or right at the end of our interval at t equals 8. So at what time t? We say t is equal to 3.272. We could write w of 3.272 is less than w of 0, which is less than w of 8. So this indeed, just by knowing that the derivative there is 0, it could be a minimum or a maximum, but the fact that it's lower than both of the endpoints, this tells us that, hey, this is a minimum point right over there. Or we could say that t equals 3.272 is where we hit our minimum value.